Hello, guys. I'd like to take this opportunity to go over these two questions. Some of you saw these on the quiz, which is given recently. I'd like to go over the couple of different methods, which has been, of course, you saw it in the recorded lectures. But as a summary, I'd also like to point out the common mistakes I saw when I was grading your work. The first method, of course, I will call it method number one. Okay. The typical step is to set up this piece equals to 0. Okay, this step is optional, but it does do certain important work. And what it does is that it identifies the points where the factors changes sign. What I mean by this is that when we apply, if this product equals to 0, right? So we said this, the intention is to identify the points which makes the product equals to 0, as we view this as the product of two numbers equals to 0. Okay, and of course, we wanted to solve inequalities such that this is the if statement we want to solve. Okay, so it's A times B greater than or equal to 0. So that's what we see as these products. So when we set the product equals to 0, we basically identify at what point of X the product is equal to 0. So now with this said and done, we apply principle number 5, right? Principle number 5 says if, right? Principle number 5, if the product of two numbers is 0, then one of them must be 0, or B is equal to 0. Okay, so principle number 5. So this is also called zero product property. So now with that in our principle that we can apply, so we would have X plus 2 equals 0, or X minus 3 equals to 0. Okay, and then we go further, we found X equals to negative 2, or X equals to 3. Okay, so this way we identify these two numbers. As I said, this part is not especially necessary if you can just recognize the number where each factor changes sign. Obviously, X plus 2, which has a domain, all real numbers, right? With the domain, all real numbers, from negative infinity to positive infinity, it changes sign at X equals to negative 2. Okay, and in terms of sign, right, if we pick any number when X is less than negative 2, okay, for any number, for any X less than negative 2, X plus 2 will be negative. Okay, for any X is larger than negative 2, X plus 2 will be positive. So for this reason, we set up this number line. Okay, we set out this number line. On this number line, there's a point where it's negative 2. So we will consider the sign of X plus 2. Okay, we'll consider the sign of X plus 2. When X is equal to negative 2, it is 0, right? X plus 2 is 0. When x is less than -2, x plus 2 is going to assume the sign of negative. Okay, I'm going to change it to negative sign. So negative. When x is larger than -2, which are if we pick up any point, right? Larger than -2, this is the number line, then x plus 2 is going to be positive. Whoops. It's going to be positive. Okay, you probably see this in the lecture. And the same thing is true for x minus 3. The only difference is that the sign would change at a positive 3. So we're going to look at the sign of x minus 3, okay? So in this regard, of course, once again, we have a number line. And on this number line, there's number S3, okay? And when we assume any value, when we pick any number x from less than 3, x minus 3 will be negative. And at 3, when x is equal to 3, it's 0. Larger than 3 is going to be positive. Right? This is the familiar method we talk about in the recorded lectures. And then, of course, the question in our consideration is that if the product is greater than or equal to 0, so next we're going to observe the sign of this product. The sign of this product. The sign of this product, of course, it changes sign at -2 at a positive 3, right? As we found over here. So this number line, and first we have -2, and then we have positive 3, and the number line continues. Right, so this product, when we pick up any number, less than -2, we plug in the product, and we will have a negative number from x plus 2 and the negative number from x minus 3. So negative times negative is going to be a positive. All right, so when we pick any number from less than -2 and plug in the product, and we ended up with negative times negative, because for numbers less than -2, x plus 2 is negative, x minus 3 is negative, so negative times negative is positive. And continue when we pick up -2. When -2 is picked, x plus 2 is 0. 0 times anything is going to be 0. And now, when we pick a number from between -2 to 3, we pick up numbers from here, we ended up with positive times negative. So positive times negative is going to be negative. And at 3, and of course this time, x minus 3 is 0. 0 times anything is 0. So this is going to be 0. And beyond 3, okay, if when we pick a number larger than 3 and plug in the product, we're going to get positive times positive. Positive times positive is going to be positive. Okay. Now by this time, we will know the solution. We will know the solution, right? Because we want all the solution that will make this inequality true, right? So we would say the solution to this inequality are all the numbers that make it equal to 0 or larger than 0, okay? And those numbers are x less than or equal to -2, or x is greater than or equals to 3. So this is the method we talk about in class. But there's another method to do this. This is a method 1, which basically we apply principle number 5 and principle number 6 to design a method to do it. to design a method to do it. In terms of how to show work, okay, the show work part, I think it can be a little, shorter. Okay, so here I'm going to show it to you. Okay, show work part. The show work part on method 1, sorry. Show work part on method 1. It can be, okay. I'm just going to make it a little shorter. I'm going to make it a little shorter here. We can, you can remove this. We can remove this. Okay. And this part is kind of optional. Okay. But but a lot of you would like to do this step. So you need to know the purpose of this step. So if you like to do this step, no problem. Just leave it there. So this will be the work you can show. Make sure your work is well organized. Your work is well organized, okay? So that will be very helpful for you and your reader. The second method number 2. Okay, method 2 is that we'll be treating this as a function. Okay? And we assume this is a function. Okay, you can assume that explicitly or implicitly. And as for this function, we want, right? The if statement says we want the product to be greater than or equal to 0. And naturally we'll try to find the x-intercepts. Okay, so the first step you're going to do is find x-intercept. We know this is a parabola that opens up, right? So to find x-intercept, we're going to set the output equals to 0. And of course, that is going to be ended up with the same thing here, right? That's what we did. You see, it's just a different interpretation. So with that said and done, we got our x-intercepts, right? We got our x-intercepts. Our x-intercepts are, of course, there's 2 points. One is a -2, 0, and the other one is 3, 0. When input is -2, the output is 0. When input is 3, output is 0. So let's see where are the points. Okay, obviously this is a parabola. Okay, and we can draw the parabola. Okay, and we are going to draw that parabola, and that parabola looks like this. Okay, looks like this. So I'm going to make a little adjustment, and these pictures are at your fingertips, right? And so let me make some more adjustments. So this is -4 here. This is going to make it 5. -7, and here maybe I make it 7. Okay, so this is the parabola. And we also know it's wait, hold on, right here. Okay, so this is the graph of the function. So where are the x-intercepts? So what are these points? And these are the points which are going to be, we can mark these points, okay, with a red dot. Okay, with a red dot. Another red dot. Okay, these 2 red dots. And we can mark them as -2, 0. And the other one would be 3, 0, right? Input, output. So when we want the product to be greater than or equal to 0, when we want the product greater than equal to 0, right? So that if statement, okay, so let me just, so you see the marking of the points, right? So if this piece is greater than or equal to 0, we know the output. We're trying to find the input. So what are the pieces where we had a positive, we have greater than or equal to 0? Well, this piece is positive, right? This piece is a positive on the curve, the output positive. And these two dots give us 0. So what are the inputs that will make that? These are the inputs. These are the inputs, right? So we have identified all the numbers such that the output is greater than or equal to 0. So from this picture, we can tell the solution would be x less than equals to -2, or x is greater than or equals to 3. Okay, so these are two different methods. So from what we learned about quadratic, and now comes to this point, Okay, so let me just make a little bit of a better adjustment about these pictures. So that way it doesn't go away, and I'm gonna do a comparison. I'm gonna make a comparison for you. Okay, so -2, 0, -10, 0. So I'm gonna make this, I'm going to make it thicker. Okay. That line, another line. So this is gonna be 3, 0, 10, 0. Okay, so then I'm going to remove all of these stuff over here. You can see from the picture, it's very clear, right? As what input will make the output greater than or equal to 0. So solution, of course, is still, so this is the solution. Okay, if we compare this picture, with what we did finally over here. Okay, so I'm going to show you. I'm going to bring these two together. Okay, bring these two together so you can compare side by side. Okay. So they're essentially the same thing, aren't they? They're essentially the same thing. It basically shows the, for what input the output is positive. And in this picture we did earlier, is that for the input less than or equals -2, the output is positive or 0. For input larger than or equals to 3, the output is positive or 0. You see, these pictures are consistent. It's just a different way of drawing them. Okay, so these are the two methods. There's another method that was commonly taught in textbook. Okay, so method 3, I wouldn't even call method 3. They're all similar. Okay, the methods developed out of principle number 5 and number 6, but we call it number 3 because the different way we present it. The different way we present it, usually we will have this step. Instead of doing this chart or graph, this third method here, okay, this third method here, we're still solving for this piece. Okay, so secretly we regard it as a function, right? We still regard it as a function. Implicitly, we're thinking of it as a function. Okay, so function concept is always very, very helpful. Okay, so with that said and done, in this method, we're making a table. Okay, so we know that there's a line, there's a number line, right? There's a number line. There's a 2 points where sign changes could take place, right? According to that, we make an interval. Okay, we make an intervals. Okay, so I'm gonna have a couple columns. Couple columns. 4 rows. 4 rows might be enough. Okay, so that we have interval. I put this method there so you have an exposure to the different ways of presentation. Okay, so intervals. One of the intervals, of course, is from negative infinity to negative 2. Okay, from negative infinity to negative 2. Here, depending on, because negative 2 is also a solution. Okay, so be careful. Negative 2 is a solution because when x equals negative 2, the product is equal to 0. And that is also a desired consequence. For that reason, we're going to set up the interval. We're going to write the interval in this way. Okay. And in between, we have negative 2, 3, which is the interval right here. And the third one, of course, will be including the 3 because 3 makes a solution. Okay, 3 makes the solution. And we have 3 to positive infinity. And then we have test points. Okay, we pick up test points. How do we pick up test point? We pick up test point always inside the interval. So for example, in this interval, I'm going to pick up negative 3. In that interval, I'm going to pick up 0. In this interval, I'm going to pick up 4. And then we're going to observe the sign of these factors, of these sign of different factors, x plus 2, right? And the next one is the sign of, sign of x plus 3. Sorry about that. Let me do it over. Sign of x plus 3. Okay, you can see the idea is very similar. This is a commonly taught method. Okay, so sign of the product. Sign of the product. We still apply principle number 5 and principle number 6. So when the test point is plug in x plus 2, you can see if we plug in negative 3 to x plus 2, we're going to get a negative sign. When we plug in 0 into x plus 2, we're going to get a positive sign. When we plug in 4 into x plus 2, we're going to get a positive sign. Okay? When we plug in negative 3 in x minus 3, that's going to be negative. When we plug in 0 in x minus 3, we're going to get negative. When we pick up 4 in x minus 3, we're going to get a positive. So when we look at the product, right, on this interval, we encounter negative times negative, that's going to be positive. And in the interval between negative 2 to 3, we have positive times negative, that's a negative. Positive times positive, that's going to be positive. So finally, which one is a desired interval? Well, we solving for inequality x product is to be greater than or equals to 0. So this one will be desired, and that one is desired. And there we go. So solution will be once again x less than equals to negative 2, or x is greater than or equals to 3. Okay, so all 3 methods, as you can see. The last method number 4. I hope you guys will watch this far. Okay, or maybe you want to take a break. Number 4, I usually don't talk about it unless I encounter those. Of course, I always encounter those. Okay. Method 4 is, I often see students doing this, but rarely I see them done correctly. There are a few times that students are done correctly, but unfortunately, most of the time it was not done correctly. Okay, so in order to cover this question, okay, so let me copy the question one more time. We reflect the meaning, right? Solve for that. Solve this inequality. Solve for x and this product is greater than equals to 0. Okay. So first of all, analyzing. Okay, this method is actually a method I was taught many years ago when I was in high school. And this method goes like this. So we view this as a product of two numbers. Okay, so A times B equals to 0, or greater than or equal to 0. Okay, greater than or equal to 0. Okay, according to principle number 6. So here I'm going to write down something. Think out aloud. Think out aloud. Okay, if this is true, okay, if this is true, what can we know? What can we guess? What are the possible cases about A and B? Right? We know that a positive number times positive, it could be a positive times positive, right? It could also be a negative times negative. So these are the two cases. Okay. So what does the first case mean? The first case means that A is positive, B is positive. And the second case is that A is negative and B is negative. So they both have to be both positive or both negative. Okay, so that is, okay, so let me write it down in words so you can have time to digest this. If A times B is greater than equals to 0, then, okay, then either both A and B are positive, or, okay, either or, okay, or both A and B are negative. Okay, so you need to pause this lesson, this lecture now to think about it. Do that. Okay. So once you understand this, okay, you have done the pause, you come back, you think about the words I said here. Okay. So there are two cases that will lead to positive product, positive or 0 product. Either A and B are both positive or both negative. That means if A is positive and B must be positive in order to guarantee A times B is positive. And the same is true. If A is negative, B then must be negative as well, such that A and B are, A multiplied B is going to be positive. So according to this statement, okay, according to this statement, we are going to write it algebraically. Both A and B are positive. Okay, so how do we write this? Either both A and B is positive. How do we describe that? Both A and B are positive. How do we describe that? This is how we write that. Okay, so let me put it down here. Okay, I made it line up. So both A and B are positive, so we would write it this way. So A is greater than or equals to 0, and B is greater than or equal to 0. The or case, both A and B are negative. How do we write that? Both A is less than or equal to 0, and B is less than or equal to 0. Okay, so if we have that, okay, so let's repeat this. If this is true, then either this one is true or the other one is true. Okay, so this step is critical. This step is critical. But in most of the cases, I see students who are trying to do this method, they only have part of it. They only have this part, most of the cases. And most of the students will forget about this case, which is you make your work incomplete. As a result, you're not gonna get much credits. Okay. All right. All right. So understanding this, so let's come back here. Right? If this product is greater than or equal to 0, of course, our A is x plus 2, B is x minus 3. So what will be the next step? Well, either this is true or that one is true, right? So if we put A in place, B in place, A in place, B in place. It should be written in this order. It should be written from left to right on the same line. Okay? And that will make a proper narrative. That will make a proper narrative. Okay? This is how you read it. Okay, this is how you read it. Okay, we can remove that. Okay, so this is how we read it mathematically. If this product is greater than or equal to 0, the next line is going to be like this. This is how you show your work. Okay, so then we keep going. You can see in this relationship is and in this piece is and. Both must be negative to guarantee the product is greater than or equal to 0. Both must be positive or 0 to guarantee the product to be greater than or equal to 0. Only this setup, if you do the logical way, only this setup is considered perfect. If you're missing this part, you're missing a lot. If you're missing this part, you're also missing a lot. Okay, so you must have both parts to make it complete work. So let's continue. Okay, so from here, we got x greater than or equals to -2, and the other one is x greater than equals to 3. And of course, we can continue to finish that other part. Okay, so here you're going to have x less than equals to -2, and x is less than or equals to 3. And then what do we do? You would have to consider these two and combine these two. Okay, remember the truth table, right? A and B is true if both are true. So for this piece, okay, I'm going to set up this. Number line. Okay. On this number line, I will have -2, and the other one is +3, of course. What is greater than or equals to -1? I'm sorry, -2. Greater than or equals to -2, I will be marking -2 itself. Okay, these are greater than or equals to -2. What are numbers that are greater than or equals to 3? Greater than or equal to 3, so the stars. Okay, for this statement and that statement to be true, both must be true. So anywhere that's been marked twice, that will be the final result of this AND. And therefore, the solution, the combination of these two is going to be x greater than or equals to 3. Okay, now let's look at the next one. For the next one, we're also going to draw the number line. Okay, and again, we have -2, and we have +3. Okay, and this time it's going to be less than or equal to -2. So what are less than or equals -2? Well, including -2, that's less than or equals -2. And less than or equals to 3. Okay, so that's going to be over here. And this statement and that statement is true if both are true. Where is both true? When both are true, only this piece. So the final solution would be the combination of these two is going to be x less than or equals to -2. Okay, I hope this helps. I hope this helps. Now, this is the proper way to solve this question using the logical way. Okay, the logical method. So if you do this logical method, okay, you must understand this is how you should be doing it. Anything short of that is either incomplete or you're missing some pieces. You're missing some pieces. For example, okay, so of course for this piece, the amount of work you have to show is just this much. You can show the number line or you don't have to show the number line. So for this method, you just have to show this much work. That's enough. That's enough, right? You can see it looks very straightforward. Looks very straightforward. Hold on. And of course, your final solution, you need to have an or, right? You have an or, and that's your solution. You're done. You're finished. Okay, you're finished, right? That's your final solution. Finished. X greater than equals 3 or x less than equals -2, which is consistent with our solution before. But you must do it this way. You must do it this way. If you want to do it this way, okay? Now, mistake. Okay, mistake I saw. Okay, so if you understand what we did here, okay, so common mistake using method number 4. Okay, oftentimes I see people only show this part. I see people only show this part. And sometimes with and is missing. With and is missing. If and is missing, that is a fatal flaw. If we don't know is or and, of course we know if you have an or there, that's a mistake. That's a mistake because in the or relationship, if one statement is true, the whole thing is true. Okay, to make this product to be true, we have to have both either positive or both are negative. So you cannot have or. If you have or, that means if one is positive, the product is positive. No, that would be a flaw. So if some people show this work with and or, you must have and to get partial credit. Okay, and of course, if you only have this, you're missing the other part. You're missing the other part. If you're missing the other part, and of course, you're missing a lot. Okay, now that's a common mistake number 1. Supposedly people, some student will do it partially correct. Partially correct. If you do it this way, right, you will get credit as called partially correct. But there's a worse mistake. There's a worse mistake. Some people do it this way. Some people do it this way. which is this is more commonly seen. Okay, they will do it this way. Okay, they will have that piece. They will write it this way. Okay, and they put an or here. Of course, that's also, this is already a mistake. This is already a mistake. Okay, this is a mistake. Now, and then the student will go about to say, they will say x is less than equals to -2, or x is greater than or equals to +3. And then the student will come and say, I get the right answer. You did get the right answer, but from this step to the next step, it's a total mistake. Okay, so from these two steps, okay, so from here to that point, you should get x greater than equals -2 instead of less than equals -2. This step is not justified. Okay, unjustified. So this is a mistake again. Okay, so you'll be graded on mistake. Some teacher might give you partial credit for this piece being right. Okay, some instructor might give you some point for it, but you certainly is not going to get all the credit. You probably lose most of the points. So it depends on the instructor's policy. But in my experience, I'm sorry, no, this is not the right place. Okay, in my experience, the more points we give you for wrong work, you have the more tendency to repeat it. So I think it will be for your benefit to know it is really bad. It's a mistake. So you should not repeat. So we will definitely, I would definitely take most of the points off. Okay, because for this mistake, in my grading policy, this mistake you should lose 3 points. Okay, you should lose 3 points. Okay, the logic is clear, right? If one of them is greater than equal to 0 and the other one is not, the product is not going to be greater than equal to 0. So that is a flawed logic. So from this step, so you'll be graded for these mistakes. From here to there, that's a mistake. That's mistake number 1. And from here, there's another mistake. So the first mistake should probably cost you 3 points. Okay. And the next mistake probably should cost you at least 1 point or 2 points. So for us to learn the lesson properly. Overall, I wish you guys to understand the inner logic of solving these kind of inequalities. Okay, so next. Okay, next I'm going to cover the other question. And this other question is solve for x, which is going to be x plus 3 divided by, is it x minus 3? X minus 3 over x plus 1 greater than equals to 0. And of course, we can also come up with different methods. Okay, parallel to the first one, right? Method number 1, we can set the numerator equals to 0. And what is the purpose? I want you to go and think about that. When we set this equal to 0, and we also set x plus 1 equals to 0, what are we trying to do? Well, we're trying to identify points. So this step the purpose is to identify points where sign change may take place, okay? It sometimes takes place, sometimes it doesn't take place. So from the first one, of course, we get x equals to 3. This step is not entirely, necessary. Some people don't do this step, which is fine. Okay, as long as you can identify these 2 points. Are they x-intercepts if we consider a function? Not necessarily, because the domain, in this case, you have to consider the domain. So x equals -3 cannot be the x-intercept, because the domain is x cannot be equals to -1. Okay, so now if we use similar method as we did before in the previous question, we will look at the sign of x minus 3. Okay, we've done the sign x minus 3 before, so we're going to just copy that piece of work, right? We copy that piece of work. And of course, in the next one is the sign of x plus 1. Of x plus 1. Okay, x plus 1. So for that one, we can, we're going to set up a number line. Okay, at a -1, there's a sign change. But at -1, the function is, the inequality is undefined. The function is undefined. So here we're going to, of course, we're going to have a negative for less than -1, and this one is going to be 0, right? So that's going to that's similar to what we did before. There's some nuances, which is we have to consider the denominator cannot be 0. Okay, so finally, we're going to consider the sign of the quotient, the sign of the quotient. It's x plus 3 over x minus 1. Okay, so in that regard, we're going to have the number line, right? So here's -1, and continue +3, +3 on the number line, keep going. Now, when we pick a number from -1, less than -1, when we pick a number less than -1, we're taking a negative number divided by a negative number. Negative divided by negative is positive. But when we plug in -1 in the quotient, we encounter a dividing by 0 case. Okay, so this case you can put infinity. Or if you want divided by 0, you put infinity. Okay, so here we're going to have the positive sign there. When we pick a number between -1 and 3, that's a negative divided by positive. The negative divided by positive, that's going to be negative. When we pick 3 and plug in the quotient, we have numerator equals 0, denominator is not 0. So in this case, the quotient is 0. When we pick a number larger than 3 and plug in the quotient, and we're going to get a positive divided by positive. Positive divided by positive is going to be positive. So finally, if we want the product to be greater than or equal to 0, the solution to the quotient is going to be x less than -1, not including -1, be careful here, or x is larger than or equal to 3. So that would be the solution. Okay, so that's the first method. Second method, okay, method 2, we can also use the graphs method. The graphing of this piece is not straightforward, okay? You need to spend some energy if you have to sketch by hand. But if you can use this, you can use a calculator, right? And we treated this as a function. And of course, we know this function. And we can graph this function pretty easily with the software. And then you have to know what to look, okay? If you know there's a vertical asymptote, right? Where is the vertical asymptote? The vertical asymptote is at x equals to -1. Okay, so let me draw that to show you. Okay, the vertical asymptote. Add an item. Oops. Vertical asymptote, I make it the red broken line, meaning the curve never touched it. And you can see there's two pieces. This piece entirely is positive, above 0. Okay, it never touched 0. And the second piece here on the other side, and we can see this point. This point is 3, 0, right? That's the x-intercept. You can also find the x-intercept. That x-intercept is 3, 0. 3, 0. So that red dot. Okay, red dot, that's a 3, 0. So let me make a little adjustment to the picture. And okay, so that picture should be proper for us to see. Okay, so that point is 3, 0. So you can see the solution would be all the pieces, right? Because this piece is a positive. This piece's output is a positive, right? Satisfy greater than or equal to 0. And that other piece, you have one point that equals to 0, 0 output and positive later, right? So the solution would be all the way here, not including -1, and all the way here, including 3 and beyond. So if I am to draw these properly, okay, so let me draw this properly. -1, 0. This is going to be red. Okay, thick. And then the other piece is going to be +3. And 10. So these two pieces. But here I need to put a little circle. I need to put a little circle there. Okay, so I'm going to put a circle. Oops. Circle at a -1, 0, indicating that that point is not included. That point is included. So that's also the solution, which is x less than -1 and x is greater than or equal to 3. So that's also a solution. In this method, which is a graph, using this method, of course, you need to have your proper graph with you. You have a graphing apparatus, or you're ready to sketch. Okay, sketching is not impossible. It just take a little bit of time. Okay, plot some points, identify the vertical asymptote. So I'm not going to spend time on the graph. Okay, just assuming that you have a graphing tool. So this is how you read the graph. And next, what you see here is that the solution, of course, you're going to say, oh, I need to identify x-intercept, right? So you also need to find, just like the question we did before, we need to find x-intercept. Okay, we don't know how many we have, so there might be more plural. In this case, of course, we only have 2. So you're also going to set the output equals 0. You set output equals 0. Okay, denominator cannot be 0. Okay, because we know the domain is x cannot be equals to -1. Okay, x cannot be equals to -1. So that's a guarantee. So for output to be equal to 0, the only way for that to happen, x minus 3 has to be 0. And of course, we get x equals to 3. Okay, so the x-intercept, we only have 1, would just be 3, 0. So which is here. Okay, so that's the x-intercept. You can see in this process, we also find x-intercept. Also find x-intercept. If you can, I hope you can see some similarities in this process. Okay, see some similarities in this process. Okay, so this is the second method. Third method, okay, third method, which is parallel to what we did before. It also has something to do with the table. Okay, so I'm going to use this table method to show you. Okay, so method 3, you're going to see this in calculus text. Okay, it's been taught that way. So when we're solving that inequality, this is method 3. And of course, we're solving, so, let's see, solve for x, right? Solve for x. Okay, solve for x. So that is the, of course, we still carry the same domain. So I'm going to just kind of copy this piece and move it down and try to make this lecture just a little bit shorter. Okay, I think it's already pretty long. So take breaks in the process. Okay, all these methods are very, very important for you to understand. Okay, so we're shooting for understanding. Okay, so we want to identify points for where sign changes takes place, and eventually we have identified 2 numbers. Okay, one is -1, the other one is +3. There could be sign changes. Okay, so we set up our table and we have our intervals, which is very similar to the method we did earlier. And these intervals are, of course, from -infinity to -1, -infinity to -1. Because -1 is not in the domain, so here we have bracket, we have parentheses instead of bracket. The next one, we're going to have this. -1 is not included, but +3 is included. And the third interval, of course, is going to be this interval, 3 to infinity. 3 to infinity, because 3 is a solution. 3 is a solution. Actually, here we can actually just make it parentheses, really. Okay. Now, test point. Test points. So on this test point, of course, we're going to pick -2, and the next one we can pick 0, and this one we can pick 4. And then we're going to look at sign of x minus 3, right? The next one, of course, is going to be sign of x plus 1. And then, of course, it's a sign of the quotient. Sign of the quotient. Okay, right here. And then you plug in -2 in this expression, we're going to have negative. And over here, you plug in 0, you're going to get a negative, right? You plug in 4, you're going to get positive. You plug in -2 in here, you get negative. You plug in 0 here, you get positive. You plug in 4, you get positive again. And negative divided by negative is positive. Negative divided by positive is negative. positive divided by positive is positive. So what are the desired interval? Well, this one, right? So we're gonna put a heart here, and this one. You can see the similarities. You really see the similarities. Okay. With that said and done, the solution, of course, is going to be the same. Solution. Oh, did I write the solution for the previous one? Oh yeah, solution is right here. So solution to that one. Okay. And the solution to this one is the same solution, Method 4. Method 4. Okay. If you also want to do the logical method, the idea is similar to what we did before. The only thing is that this time is for division. Okay, so remember the narratives we have there for logic? So I want to copy and paste here so you can see the comparison. Okay, you can see the comparison, which is over here. Okay, so I'm going to still put it in think out loud. Instead of multiplication, this time is division. And of course, we have to think of that, oh, we have to make sure denominator is not 0. Right? We have to make sure the denominator is not 0. And everything else is pretty much the same, right? And denominator cannot be 0, and which we already guaranteed, right? B cannot be 0. So there's an added there's an added layer of consideration. So just like when we divide, when we multiply, dividing, if the quotient is positive or 0, then same story, both are positive or both are negative. Either A is greater than or equal to 0 or B is greater than 0, but here B cannot be 0. B cannot be 0, right? So B has to be positive. And the other one is A is less than or equal to 0, B is less than or equal to 0. So here B has to be less than 0, right? So with this quotient greater than or equal to 0, so we have a slight change in consideration, all things considered. Okay, so then we're going to bring these to bring this statement, okay? So if this is true, right, then we know this is an if statement. And what will be the next statement? We're going to copy this piece and forming our work. And A is x minus 3. So this is going to be x minus 3. And B is x plus 1. Right? And this is x minus 3. And this is x plus 1. I got a capital there. Okay. There we go. Okay, so let me just make some space between these OR cases so they're not so squished together. Okay, so here on this side, we're going to have x greater than or equals to 3. And we're going to bring that logical connection with it. So x is greater than -1. Or on this piece, we will have x less than or equals to 3 and x is less than -1. So once again, we're going to figure out what is the combination of the two and what is the combination of these two, right? A and B is true if both are true. So we use truth table. So here we got -1, right? We got +3, and the number line continue. And of course, we know that we need 2 number lines, right? Whoops. So we need 2 number lines. Whoops. 2 number lines. Okay. So this number line is for the first part before or, and the other one is for the or, right? So we have both at our disposal. So greater than equals to 3, greater than equals to 3, it will be including the 3 and greater. And greater than 1 does not include -1. So it's just this piece. Right? This statement and that statement is true if both are true. So the combination, the result of combination is going to be x is greater than equals to 3. Okay, because only this piece is shaded twice. Shaded twice. Okay. And the second one, the same is the same story. Less than or equals to 3. So here less than equals to 3, including 3, and less than -1. Less than -1, not including -1. So less than -1. So which part is being shaded twice? Less than -1. So the final solution is going to be x less than -1. And they're connected by or. They're connected by or. Okay. The final solution. Okay. So our final solution is this piece. That's our solution. That's the solution. Okay. So that's, let me do it over. Okay. So make it thinner. Okay. So here's our solution. I'm going to box the solution. The box solution is like that. Same as before. So here's the logical way. All 4 methods for 2 questions. I hope this helps. Okay. Thank you for watching. Until next time. Goodbye.